Hello, everyone. Welcome back to today's lecture number 6, where we're going to talk about the theorems of existence and the complexity of Nash equilibrium. So first, we talk about the labeling symmetry of the voting game. In fact, the voting game model is intrinsically symmetrical when we do some sort of flipping operation. Let's say we got individuals I and J1, J2, each individuals with respect to each feature. So that let's say feature F1, we got a choice 0, 1, or 0. We can calculate the weighted sum for individuals I, and it is a number that's calculated based on the choices of its neighbor. Whether it is greater than tall or not will affect the voted results. And we'll see whether the voted result matches the individual's results. Now let's do one thing. Let's consider a mirrored model. So instead of 0, each 0 becomes 1, each 1 becomes 0. So that in this case, the weighted sum will be flipping as well because of this sign. It will becomes di minus the weighted sum. And if we choose the threshold level identically to di minus tau I as before, we will see that these two models are exactly the same, meaning that if one model has weighted sum greater than the threshold level, the other model will be having a greatest weighted sum smaller than the threshold model. The two models are functionally the same in a mirrored way. For more details, and we got a complete proof in the paper version. What does that mean? Is that the application of this symmetrical claim is it can be used as a symmetry breaking constraint for the mixed integer linear programming. And it can be helpful to implement it to accelerate the calculation process. Next, we can talk about the existence of a Nash equilibrium. So like in game theory, a Nash equilibrium is a strategy, let's say X and tau here, such that for any individual, it is not possible to find a better strategy by unilaterally change one individual's strategy. So this strategy, the Nash equilibrium strategy, is always better than any other strategy that is available to the individual I. And for this paper, we establish a big sections contributed to characterize the existence of the Nash equilibrium. There's no sufficient conditions on, we establish a sufficient conditions to characterize the existence of that by using a path-like characterization process. I can give you an example of what a very toy example of what Nash equilibrium can be like. Let's say we got two individuals, I and J, and I is friend to J and J is enemy to I. Let's say in this case. So let's say J chooses 0, right? So based on I, the weighted sum of I with respect to feature F, but we sum up all the enemies point is going to be 0. So it must be smaller than tau I. I is suggested to vote 0 as well, right? And so if I vote 0, that's calculated the weighted sum for J, right? So J has an enemy that votes 0. It gives the weighted sum to be 1. So the weighted sum is 1 and the threshold is either 0 or 1. It is always, so the weighted sum is greater than the threshold, for J. So means that J is suggested to vote 1. So you see in this case, J is not, how to say, this is not a perfect solution for everyone. You cannot satisfy everything at the same time. However, this is an example that this situation can happen. Now let's talk about how hard it is to solve such a problem, the problem of finding a Nash equilibrium. We prove that it is amply complete. Um, the proof will be fully available. It's a long, very long proof in the paper version in the PDF. Basically, we are trying to reduce it into we reduce a three satisfiability problem into a voting problem. So that if we know that three sat is a NP complete problem, it follows that our voting game model is also as hard as that. In the next slide, let's talk about why it is like three sat. So three sat is like the case where you got variables, let's say x1 and not x2 and x3, or another phrase like that. This is called disjunctive normal form, a Boolean expression. And the objective is to find assignment. So x1 it is true or false, x2 it is true or false, etc. Find assignment where it makes the whole expression to be true. We're asking ourselves whether this kind of assignment can exist. And in the voting game, we can kind of do the same thing by introducing players um, as nodes that represent the variables. So x1, x2, and x3 can be different nodes, and the first clause can be a node. And we can say if this is a positive, then the clause one is friend with that variable, and it's enemy with the second variable because it's negated. It's friend with the third variable, etc. And we can prove that um, the problem of whether this is satisfied and the problem of whether this is a, how to say, an Nash equilibrium solution is two problems that are similar to each other. They are either both true or both false. They are equivalent. And based on this transformation, we established the fact that the voting game, at least the direct voting game, is a NP complete problem. We have already mentioned the difference between the Nash equilibrium and the social welfare. Nash equilibrium, we only care about whether individuals cannot single-handedly improve the solution. The social welfare is among all the possible strategies of individuals, what is the strategy that maximizes the sum of all utilities? And we know that in strategic settings like international politics, we care or the Nash equilibrium makes more sense. It provides a better fit for the observed data rather than the social welfare solutions because each individuals um, try to optimize his or her proper utility. We cannot assume that individuals want to maximize the utility for the whole community, assuming that they know the utility of others, etc. So in most cases, Nash equilibrium is the tool that is better suited for that. In summary, this voting game is labeling symmetric. You can flip the signs. The whole game becomes the mirrored version of the other game, and these are equivalent to each other. Secondly, the solution that is in the Nash equilibrium is a NP-complete problem. It requires an advanced optimization process to tackle this. And also the Nash equilibrium is a better suited tool for the application purpose for the network observations, patterns, etc. So thank you for watching and see you guys in the next lecture. Bye bye.